So you have been able to stay this long with the algebraic topology. I know that the kind of material we are covering is quite unusual to engineering literature, but still I think once you see the entire Maxwell equation in the way I promised without vector calculus or differential equation will be a good relief in itself. So with that promise I am going to take you to the last part of the algebraic topology, which will be on the time orientation and the concept of Maxwell equation itself modeled using the different tools which we have created. So with that, let us start the time orientation. So what do I mean by time orientation? This slide might not make any sense before I give you a little bit of a story from mechanics. So let us take an example. Let us assume that we are talking about a body that is moving from left to right, and let us say it is at time instant t equal to 1, it is at point x1, at time t2 it is at x2, at time t3 it is at x3. So what we have got is the time duration, let us say we call it tau, is equal to t2 minus t1, and let us assume that it is also equal to t3 minus t2. In other words, we are talking about the time duration that is equal between these two observations. So based on that, we can compute the mean velocity while the body is moving in this direction at this point between x2 and x1. So the mean velocity we write 1 is equal to x2 minus x1 divided by tau. So this is the mean velocity. Let us say we are computing the mean velocity between point x2 and x3. So it will be given by v2, which is equal to, so this is v1, this is v2, which is equal to x3 minus x2 divided by tau. So for these 2 points we can also compute the acceleration based on these 2 things, because we have got 2 velocity, so we can compute the acceleration. In other words, we can say mean acceleration is equal to v2 minus v1 divided by tau. If you substitute the value of v2 and v1, you will get an expression for acceleration which is x3 minus 2x2 x1 divided by tau square. So this is the basis for us to talk about something very unique about time, which normally in engineering literature we do not make use of. So what we are going to look at is, we have got an expression for mean acceleration and mean velocity. We said we are going from point x1, x2 and x3. So we are going like this. So now what I am going to do is, I am going to reverse the motion. So the motion is going to be reversed. In other words, we are going to change the order in which the point are going to be seen by the object that is moving. In other words, x2 will be our starting point and we are moving towards x1. So this is the concept of motion reversal. So when we do the motion reversal, what we are doing is, we are kind of going in the opposite direction to that of the former direction. So the order in which the object is going to see the things will be different. So it will see at t1 x3 T2 it will see x2 and T3 it will see x1. So when that is being happened, let us see what are the values of v and acceleration. So when we compute that, let us say we are computing under the motion reversal, I am using the word motion reversal m. The first one will be x1 minus x2. If I say this is going to be the motion reversal velocity, so it will be x1 minus x2 divided by tau, because in this case the object is going to go from x2 to x1. Similarly, we will have Vm2 is equal to, here in this case initially we called this side, the object is going from here to here, we computed the Vm2. Now we are going to compute Vm2 when the object is going from here to here. So in other words, we will get x2 minus x3 divided by tau. Nothing is happening to tau, tau remains the same. So what we are getting here is, when you compare this one to the value that we have computed here, we are able to see that this value and this value are opposite to each other. We have x1 minus x2, whereas here we have x2 minus x1. So this is, we can write, is equal to minus v1 and this is equal to minus v2. So this is about the motion reversal. So let us consider what happens when we do not do motion reversal and we do just time reversal. So time reversal is nothing but a purely mathematical thing. It has nothing to do with any physics. In motion reversal there is a physical meaning. Instead of going in one direction, you are going in the opposite direction, whereas time reversal is purely mathematical, where you are putting instead of t minus t. So let us put the thing and see what is happening to velocity and acceleration. So what we have got now is, we said we call time reversal is t becomes minus t. So when you have delta t, where we have to use the thing minus delta t. In other words, what we will have is minus tau. So what is happening now is, the value we call velocity with t is for time reversal will be equal to x2 minus x1 like before divided by minus tau. So instead of tau we will have minus tau. Similarly, Vt2 time reversal velocity 2, this you can see from here, instead of tau I am using minus tau. So similarly for Vt2 I put x3 minus x1, instead of tau I use minus tau. So these are nothing but the minus of V1, this is equal to minus of V2. Let us see what is happening to acceleration. So acceleration under time reversal is equal to Vt2 minus Vt1 divided by minus tau. As you can see, this minus tau will cancel off with the minus tau that we have on the numerator. So what we will get is nothing but x3 minus 2x2 x1 divided by tau square, which is nothing but the same expression what we have got in the initial case without any time reversal, which is a. So what is important to see is, under time reversal and motion reversal, the value of the velocity changes to minus, whereas the acceleration does not change its sign under motion and time reversal. So that being said, there is something unique about the time that we are associating to velocity and acceleration. So we cannot associate the same time for acceleration and also to velocity, because we saw when we do motion reversal, the value of velocity before motion reversal and after motion reversal, they are exactly opposite. Similarly, when you do time reversal, they are also opposite, whereas acceleration doesn't care, it doesn't change when you do motion reversal or when you do time reversal. So there is something unique about the way in which acceleration is associating itself with time. So that gives us a kind of a motivation or a hint that the time we are talking about are not the same time. When it comes to velocity, it is associated with one particular time. When it comes to acceleration, it is associated with one particular time, and that is what we call it as inner and outer orientation of time. So here you will see in this case in the slide, I have a normal case where I have a time duration and I do the motion reversal, so my time duration is oriented in the opposite direction, but still the time duration will be within the same limit, but the orientation is going to change. Whereas when you see that inner oriented time duration, so this is the inner oriented, this one is the outer oriented. So the inner oriented time duration changes direction, so it goes from this side to outside, whereas the outer oriented time duration is pointing inside, and then when you turn 180 degree, it will still be, the arrows will be still pointing inside. So this is what we call it as inner and outer orientation of time. So the inner orientation of time will be always oriented towards that point. So for example, if we call Tn as the time instant, the inner orientation of time when you rotate the time will still be the same. So it always be the same point, the arrows doesn't change direction. Whereas in the case of the outer oriented time, the time duration is going to change direction, and the time instances, the point along which it acts, it's also going to change direction. So this is the motivation that we have to associate the velocity to a kind of time orientation and the acceleration to other type of orientation. In this slide what you can see, velocity will be associated with this time orientation, which we call it as outer orientation, and the acceleration is going to be oriented to the inner orientation, where even if you change the direction, it doesn't make a big difference. So this is the motivation for us to understand that time also has two different orientation. Now we will see one of the main reason why we are doing leapfrogging. You remember in the case of doing finite difference time domain, we did leapfrogging in time. We never asked the question, why are we doing leapfrogging? The leapfrogging is basically having two set of time instances and time durations that are called as inner and outer orientation. One of them will be called as the primal time, the other one will be called as the dual time. So the primal time, where the components can change, even if you change the direction, the components will not have any impact, or the outer orientation, when you change the direction, the object will have certain changes, like we saw in the case of velocity versus acceleration. So in this slide you can see algebraic topology gives you an intuitive reasoning why we should do leapfrogging in time discretization, because the electric field and the magnetic field, they are not the same kind of variables. One of them, when you reverse the direction, changes sign, whereas the other one does not. So that's why you have to use them in two different time instances. So I have given you now almost everything that you need to know about algebraic topology except one thing. We have not yet modeled the Maxwell equation the way I promised you before. I said we are not going to need any vector calculus and partial differential equation, and that is exactly what we are going to do now. So let's go into the Maxwell equation with the theoretical framework what we have got. So we will see we have got various variables, charge content written as QC, the charge flow written as QF, the electric flux written as psi, Magnetomotance written as capital U, electromotance written as capital V, and magnetic flux written as the capital phi. So what we are seeing now is all these variables are scalar quantities like I said before, and they have to be associated with certain spatial orientation and a time orientation. As you can see, the charge will be oriented with the dual volume and the primal time instant. Likewise, the charge flow will be oriented with the dual surface and the primal time duration. So all the things that we call as the source variable related to either electric or magnetic sources, the charge content, charge flow, magnetic flux, magnetomotance, they are all connected to the dual volumes and the primal time. So the volume, the surface and the line aspect are in the dual space for the source variables, whereas the time components are all in the primal space. So there are no tilde, so they are time, t is a time instant, tau is a time span or the time duration. Likewise, we have got the configuration variables where we call them electromotance and magnetic flux. They are related to the primal space and dual time coordinates. So V is measured on the primal line and the dual time span. Similarly, the magnetic flux is calculated on the primal surface and dual instant. With this as a motivation, we are going to do now the Maxwell equation one by one. So let's start with the most easiest one, the Gauss law. We have got now the divergence of D is equal to rho. So let's write this one. I am going to do the volume integration on both sides. So I do I am just integrating using the volume inside which I am interested in doing this. So by doing this, I know from the previous case this thing, the integral V rho dV is nothing but the charge content. So this is what we did in the first modules on algebraic topology. This is the definition of the charge content, which is integral rho dV. So QC and rho and dV are related to this side. On the left hand side, what we have got is something that we need to do a little bit more of tweaking. So what we are going to do now is we take the divergence outside and then we have got volume integral dV. We know that we can change this side from a volume integral to surface integral using the Stokes theorem. So what we are getting now is the surface and the normal component of the flux that are passing through the surface. So this is the normal component and we are interested in the surface. So this is nothing but, we can write this as equal to QC, and we will see how this is related to, because this term is something that we already saw. We know that this term is our definition for the electric flux. So we can write this term in a much more simpler form, that is divergence of the flux is equal to QC. But using our earlier understanding that this term can be represented using the co-boundary operator. We said the divergence will be the third co-boundary operator. So what we have got is A 3 so these are all matrices. And that is what you have got in this case. When you see the slide here, what you have got here is this term is the A3 matrix, and since the electric flux, what we are calling here electric flux, in the previous slide we said it is associated to the, so the electric flux is associated to the dual surface. Since it is in the dual space, we are going to have a tilde on the top, and that is what we are having here. So if you look here in the slide, this is the dual space, because this is related to the dual space, and they are all related to the dual space, and that is what you have. If you write it in the individual form, this is the matrix form, and the individual form will be the sum of over all the sides of the volume. So L will be A, let us say ML, well M is the volume we are talking about, and then we will have phi that is defined on that particular surface. Since it is a dual, I put a dual sign, and it is associated with the primal time instant. So what we are talking about here is, this is the same, the right hand side is the same one. What we have got here is, these are the sum of all surfaces that are enclosing this volume M. So when we do this, we are getting the same equation, and this is equal to QC, which is defined on that control volume, and this control volume is in the dual space, and it is calculated at the primal time. So from the divergence equation here, we are able to see how we have come to this form, and this is the Maxwell equation for the Gauss law, only using algebraic topology, without vector calculus, without any differential equation. So now let us look at what we have got for the magnetic Gauss law. So right now we have looked into the electric component, so let us look at the magnetic Gauss law. It is very simple and straightforward. We have got, like before, the divergence of B so when you do the volume integral on both sides, we will got so I am going to take out the divergence outside, and then I am going to talk about integral B dV on the volume will be equal to 0, and I can change this from a volume integral to a surface integral. The normal component of the B on the surface is equal to 0, and this term is my definition for the magnetic flux, and this one I know is the definition for my A3, and since they are belonging to the primal grid, so remember in this case the magnetic flux is in the primal surface, so I am not going to use tilde, it will be without a tilde, and the time instance is always with a tilde. So that is why we will get now the counterpart will be ALM and without a tilde, and then phi, which is also without a tilde, and the counterpart will be the time duration, which is the dual space. So this will give you the Maxwell equation for the magnetic Gauss law without using vector calculus, and as I promised, without using differential equation. So what we have got now is, we have got the two equations, namely the Faraday's law and the case of Amperes law. So let us now look at the Faraday's law. So the Faraday's law is the curl of E is equal to minus dB by dt. I am going to do on either side a surface integration. So I will take the curl out, I do E ds around the surface minus dB by dt B ds. So what I have got here is the flux term, this I know. This is my definition of the flux, magnetic flux. On the right hand side I can use the Stokes theorem to convert the surface integral into a line integral. So what I have got here is the curl will become the line integral, and I will be talking about the tangential component of E times dl is equal to minus d phi by dt, and I know this one is my definition for the electromotance. So what I am going to have now is I am going to have a simple equation that will give me that the curl of the value V is equal to minus d phi by dt. So I can write this one as d phi by dt, and this term will be the counterpart of the curl. Curl will be the second co-boundary operator, and you have got V, and I will take the dt on the other side. So I will have dt here will be equal to minus d phi. So what you have got now is I have to integrate it on both sides to get the equation only in terms of phi. So I do the integration. So when you do the integration, what you have got is you have got a volume integral of V dt. So the volume integral, let us write it as V with an inclined V, and this is A2, and this is equal to the value that we are computing at two different points. So at time Tn and time Tn plus 1. So along when you are integrating, this is what you get, and that is what you have got here in this equation, that you have got the right hand side, which is basically the curl formulation, and then you have got the time integration of V, which is here, and the minus sign phi magnetic flux that are calculated at two different time instances, time instances t n plus 1 and t tilde n. So this is an equation that has no vectors and only using the scalar quantities and no differential equation. The last equation will be a very similar one. In the case we call it Amperes Maxwell's law, where you will see the curl of H is equal to ddt plus j, and when we do the same way, when we do the surface integration, what we have got is the j surface integration will become the charge flow, and that is what you have got here. So the j will become the charge flow component here, and the dt by dt will become the electric flux component like we did for the earlier case. And on the right hand side we will have the time integrated value of the magnetomotance, which is given here, and you have got the value for the curl, which is the boundary operator on the dual space. With that we are coming to the end of the algebraic topological model. What we have done so far is we have basically used our understanding of topological parameters to model the entire set of Maxwell equations only using scalar quantities which we can tangibly measure and also get a sense of their association with certain topological quantities. With that being said, we have covered the entire gamut of all the tools that you need to model Maxwell equation using algebraic topological methods. With that being said, I thank you for your attention. Let us see in the next modules. Thank you.